Hi, and welcome back. So in this video, or I should say in the last video, we were talking about different isotopes of hydrogen and how we could say how we would represent them and how, by definition, in order to have an atom of hydrogen, we have to have one proton in our nucleus. But the number of neutrons in the nucleus, if we had a varying number of neutrons, we could get different isotopes of hydrogen, and then that would change our mass. And actually, I should say that this hydrogen one, I think I mentioned in the last video, this is going to be this is the by far it's the most abundant isotope of hydrogen that we find in nature, and I'll definitely talk more about that in this video. And one of the other things that maybe you might need to know at some point in your chemistry course is that this isotope, hydrogen 2, is also called deuterium. So, deuterium. I know that was a question on a chemistry test I had during my chemistry class. So hydrogen 2. So that's a hydrogen atom with one proton and one neutron is also known as deuterium. But anyway, and this exists in much less percent abundance. It's much less common in nature to find. So now what we're going to talk about I keep scrolling all the way down. What we're going to talk about in this video is about how, if you remember from the last video, I said that it's kind of weird that we should get for the atomic mass on our periodic table. It's kind of weird that we don't get a whole number, that we get 1.0079, because the atomic mass is just supposed to be, it's in AMU, and it's just the number of protons plus the number of neutrons. And the reason that this is, and perhaps I should have chosen a better example than hydrogen, because hydrogen, it's even a little bit different on top of this, but the reason that this is not a whole number is because this number is a weighted average of all the different isotopes of hydrogen that we would find in nature. So we've got, and the two most prevalent, and even there are a bunch of other isotopes. So there's hydrogen 5 and hydrogen 6, and I think even hydrogen, I think it goes up to like hydrogen 7 or 8. But pretty much above deuterium, hydrogen 3 through 8 is very unstable. It immediately starts breaking down. Some of them have half-lives of, I think, of microseconds. As soon as it's formed, it immediately kind of breaks apart. So, but deuterium is stable, even though it exists in very small percent abundance. And hydrogen 1, or I think this is sometimes called, what is it called? It's proteon, or I forget what it's called. Anyway, it's normally just called hydrogen. It's the most common isotope of hydrogen that you have. And the percent abundance that these exist in nature, so hydrogen 1, this is, if we just had, and essentially the thing that you should think about, and this is really going to be very much if you're going to do labs in your hydrogen class, you can kind of think about it this way, is if you just have, a randomly collected, balloon, let's say, you just had a randomly collected batch of hydrogen in this balloon. Some of these hydrogens are going to be hydrogen 1, so they're going to be, we'll just call these the red hydrogen. So some of the hydrogen are going to be hydrogen 1 in this bag. But some small percentage, some very small percentage, are going to be this hydrogen 2, this deuterium. So we'll say that these are going to be, actually let me choose I guess I'm doing this a bit in the inverse here, but these blue dots, there we go. So these blue dots, we could say, are our deuterium. And we can see, and this is just a very simple, probably inaccurate representation, but they exist in much less percent abundance in just a random collection, if we had a balloon that was filled with hydrogen, and you'll probably do if you're taking a chemistry class, you'll be collecting hydrogen gas over water. Specifically, if you react a metal with an acid, this is probably what you'll get. You'll get hydrogen. You'll get a collection of hydrogen gas, and it's important to understand that most of that hydrogen gas is going to be this hydrogen 1. But some small percentage of it, some very small percentage, is going to be this hydrogen 2, or deuterium. And so now you might be wondering, well, what are those percentages exactly? The percent abundance of hydrogen in nature, of hydrogen 1, is going to be 99.985%. That is how, 99.985 times out of 100, I guess, that you choose a hydrogen atom in this balloon, it's going to be hydrogen 1. And only a very, very small percentage, only, get my color, there we go, only 0.015% of the time that you choose an atom in this bag are you going to find deuterium. So you can see that, there is, this hydrogen 1 exists in much greater abundance than hydrogen 2. And essentially what this number is down here, what this number is for the atomic mass of hydrogen, is it's a weighted average, is based upon these percent abundances, based upon, I'll write them down again, based upon the fact that hydrogen 1, I'll just call it, here I'll write it all down. Hydrogen 1 has got a 99.985% abundance, and hydrogen 2, or deuterium, so hydrogen 2 has got a 0.015% abundance, based upon weighting those two averages together and then figuring out what the average molecular, or I shouldn't say molecular, what the average atomic mass is for a given atom inside of our balloon of hydrogen. If we were going to collect a balloon of hydrogen, that average atomic mass is going to be 1.0079. And if you do plug this in, it actually does something. For hydrogen, it's actually a little bit more difficult to figure out, partially because hydrogen is, if you look at the rest of this periodic table, I might be getting a little bit ahead of myself, but hydrogen is the lightest atom. It's the atom with the smallest atomic number. All of these other atoms, you can see that, the atomic masses, scandium's atomic mass is 44.956, manganese is 54.938, and let's see what the heaviest one is. Well, the heaviest ones, I guess these all are very unstable down here, but lead, we have a 207.2 atomic mass. So, they get very heavy. And essentially, for what happens for this number for hydrogen, in order to figure out the atomic mass, and if you actually plug this into the calculator, and we'll do some examples of finding out the actual atomic masses for maybe some other elements. But if you were to plug in 99.985 and figure out the weighted average for hydrogen, you wouldn't get exactly 1.0079, partially because the unit for the atomic mass unit doesn't exactly equal the mass of one proton and one neutron. So if we were going to plug this in, and let's actually, I'm going to do this right now. So essentially, if we were going to figure out the weighted average of this, and this is just a little bit of an aside, and we're not going to get this number exactly, mainly because the unit of the atomic mass unit isn't exactly equal to one proton or one neutron, but this will at least give you the idea of what happens. We're going to say, okay, so our hydrogen 1 has got an atomic mass of 1, right? Because it's just, our hydrogen 1 is just that's its atomic mass. It just has one proton. and then 99.985 times out of 100 that we choose a hydrogen atom from, you could say, a random collection of hydrogen, like we have in this balloon up here, we're going to choose this hydrogen 1. So then that is our first isotope of hydrogen. And now we could say that out of that to make up get it up to 100%, 0.015 times out of 100 that we choose an atom in this same balloon, its atomic mass is going to be 2. So we're going to have this hydrogen 2, or this deuterium we're going to find in our random collection of hydrogen. So if we were going to add that up, that would give us essentially, and this isn't going to give us exactly the right answer, mainly because, like I said, the unit of atomic mass unit, which is what this number is in atomic mass units. The unit for atomic mass unit does not exactly equal the mass of one proton or the mass of one neutron, and that's partially because the mass of a proton isn't equal to the mass of a neutron. So it's a bit, and hydrogen being the lightest element, there is a bit more room for error. So anyway, let's actually just figure this out real quick. So if we said, just to show you, so we had 99 times, so we say 99.985 times, 99.985 times out of 100. We choose this mass of 1, and then we're going to add that. So we add plus, and I'm just going to multiply this 2 first. So we say plus, I'll do parentheses, 2 times 0.015 times out of 100, close parentheses. We get, and I told you that this number wasn't going to exactly equal the atomic mass that we have on the periodic table, but essentially this would be our weighted average if the atomic masses of hydrogen 1 and hydrogen 2 were exactly 1 atomic mass unit and 2 atomic mass units. Our atomic mass would be 1.00015. So I'll write that down for right now. So we could say that this is equal to 1.00015. Even though that isn't right. I'll do some more examples in the future where we're actually going to figure out the atomic masses and how they're reported on the periodic table, and hopefully they'll actually be the correct atomic masses in the future. For right now, the big thing I want you to take away from this video is that all of these atomic masses on the periodic table, the reason that they're not, or the main reason that none of these are going to be whole numbers, the reason that they've got some weird decimals on them, is because all of these numbers, they're all weighted averages. So all of these are weighted averages of all the different isotopes of these different elements that we have. So, sodium, it's, you can maybe see that we can probably say that sodium's most common isotope would probably be sodium-23. So, we can see that this number for our atomic mass of sodium is very close to 23. It's 22.99. So we could probably say that the most common isotope of sodium would look like this. Our mass number would be 23, and our atomic number is 11. Similarly, we look at calcium. Let's look at calcium down here. So calcium's atomic mass number is going to be 40.078, and calcium's atomic number is 20. So we can probably say that the most common isotope of calcium is going to be calcium-40, right? So we have 40, 20. 20 is the number of protons in the calcium atom. 40 is the number of neutrons. And similarly, how many in this isotope? If we had this isotope of calcium, we had calcium 40 here. How many neutrons do we have in this atom? Well, we've got 20 neutrons, right? Because we know that this number, our mass number, this 40 here, is going to be our it's going to be the number of protons we have in an atom, and in order to have a calcium atom, we have to have 20 protons plus the number of neutrons. So we know that, well, what's the, we subtract out the mass of our protons, 40 minus 20. That means that we have 20 neutrons in this atom. How about this sodium atom? We figured out that our most common isotope of sodium is probably going to be sodium 23. How many neutrons are going to be in sodium 23? Well, we know that 23 is going to be equal to the number of protons. See, my pen tool just froze a little bit. There we go. We know that 23 is going to be equal to the number of protons plus the number of neutrons. And we know that we have got 11. My computer's starting to weird out on me, sorry. We know that we've got 11 protons, right? So we could just subtract 11. We could say that 23, sorry, this computer is starting to slow down. 23 is equal to 11 plus the number of neutrons. So we would subtract 11 from both sides to figure out the number of neutrons in this sodium isotope. So we would subtract 11. That gives us 12. 12 is equal to the number of neutrons. So this sodium isotope, and we could say with a good amount of confidence that it's going to be our most common isotope of sodium, is going to have 12 neutrons. So anyway, hopefully that makes sense. If it doesn't make sense, please leave comments, and I'll try to maybe record some more videos. In the future, we will definitely do probably well, we won't probably do them. We will definitely do some more examples where we figure out the actual weighted averages for these different atomic masses of the different elements, and we will also do a whole bunch more examples where we're figuring out the number of neutrons and the number of protons and the number of electrons in different isotopes and different atoms. So anyway, thanks so much for watching, and I'll see you in a future video.